At this point in our unit of study, you should have a good appreciation for free body diagrams, but you might still need a little bit of practice in developing them and seeing how to come up with the relative size of all the vectors that you're naming in your free body diagrams. The first couple examples, 1 and 2, are already done for you. So they reference that it's a static case, meaning it's an object at rest, and the problem just involves, in every case, 1 through 12, a stone. Well, remember that weight is a force. So every stone has mass, therefore weighs something. The weight is calculated as the product of mg. So that force is going to show up in every one of these free body diagrams. If the rock is hanging from a string as shown here, then one of the forces we diagram is a tension vector in the rope. Okay? If the rope is attached not only to a ceiling by a string, but it's also attached to a wall, then we can have two different tension vectors. Maybe one of them we label as tension subscript A, and the other is tension subscript B. The weight is still calculated as mg, and all three of these vectors have been drawn to the correct length. You might be able to see that in a problem like this one, tension A could be broken into components. One component would point up, but of course that would just cancel out the weight vector. And then there's another component of tension A pointing to the left, but you can see that component would cancel with tension B, so this would indeed be a static case. All right, so we've got to do part 3. Without a doubt, there's a force of gravity that can't be ignored. So there it is, weight, which is equal to mg. Now, if both strings point at an angle, then there's a tension in that piece, and there's a tension in this piece. Now, exactly how long should we draw these? Well, we can use that parallelogram method. So if we make a line through the tip of this vector that runs parallel to the other string, and we make a line through the tip of this vector parallel to the other string, then we can reproduce the vector I just crossed out. As long as we draw something pointing in the same direction and of the same length, we've reproduced the same vector. So maybe we call this one T subscript L for the tension on the left. We had T subscript R for the tension on the right, but we scribbled it out and reproduced it here. So putting those two vectors tip to tail gives us an idea of the result of those two vectors added together, which would be this one. And you can see that that red vector pointing up is about as long as the green vector pointing down, which would be a good description, again, of static equilibrium. Okay, so what if the two vectors are not, or the two strings, are not of the same angle? So in other words, in case number 4, what if we have a weight vector mg pulling down? Then which tension is greater? The tension in the left rope segment or the tension in the right segment? Well, let's try this. What if we suppose that the two are equal in magnitude? So what if I draw T subscript R just as long as I draw T subscript L? Well, if that were the case, notice what would happen along the x-axis. The component of T subscript R to the right would definitely be longer than the component of TL to the left, and so that would not represent a static case. This would be an object that would accelerate to the right. So we must have it wrong here. The only way you could have equilibrium is if the tension in the more vertical string is greater in magnitude and the tension in the less vertical string is slightly less in magnitude. If you imagine making a resolved free body diagram, the weight vector doesn't need to be resolved into components. It already lies along the y-axis. Then we have a component due to the tension in the right segment that points to the right, but it also has a component that points up. So we can call this TRX, the tension from the right string segment along the x-axis, and we have TRY. And we also have a TLX and a TLY. Now we can see that the tension in the right string and the tension along the x-axis from the left string cancel each other out, and their two vertical components would add together to offset the weight vector. Okay, by the way, this same exercise is provided as a worksheet in the folder for this unit of study. So I'll leave it up to you at this point to hit pause and attempt to make free body diagrams for the remaining cases on your own. But you can come back to this video just so that you can check out the solutions. So without giving lengthy descriptions on all these, I'm just going to draw in the free body diagrams for the rest of the cases. But please, at this point, hit pause and try it on your own. The weight vector points down. There's contact, so there's a normal force that points up. Those two have to be of the same length. There we go. Sliding at constant speed without any friction. Well, there's no distinction between static, meaning at rest, versus constant speed. Those are both cases of equilibrium. So both case 5 and 6 should have the same free body diagrams. There's no difference when it comes to forces between staying at rest or moving with constant speed. However, motion with acceleration definitely requires an imbalance in forces. All right. The common misconception is to think if it's sliding to the right, then there must be some force propelling it to the right. No, you'd only need a force to the right if this object were accelerating in that direction. If the velocity is constant, the acceleration is 0, and no force is required. Now, was there a force required to the right to get it to start moving? Yeah, probably. But once it is moving, you can take your foot off the gas pedal, so to speak, when it comes to the forces. Decelerating due to friction. So I think these little squigglies right here imply that the motion, the velocity, points to the right. But it's decelerating, okay? So the forces involved, you know well, mg points down, contact with the ground or normal force points up, and then there's some friction. So there's no, even though it's moving with velocity to the right, there's no force to the right, and indeed there's actually a force pointing back to the left. And that's the friction force, and that's why it slows down. The object is at rest on an incline. The one vector that seems to be the same in every case is mg. On an incline, the normal force doesn't point straight up, it points perpendicular to the incline. If those were the only two forces, it would be accelerating down the incline, so there must be some frictional force back up the incline to keep it at rest. If it slides without friction, well, without friction means the same forces are here, mg and n, except for there is no longer the friction force. So that's it. Number 10 says this represents a static case or an object at rest. Gravity pulls down. Normal force is perpendicular to the incline. In this case, I'm going to call it n subscript g to mean normal force from the ground. And then we'll say this is B for a block, and it's touching a block of wood. So maybe there's no friction, but that block of wood pushes back this way against the rock. But that's a contact force. That's not friction. That's not air resistance. That's another normal force. But this is N subscript B. Okay, a rock in free fall. Isn't free fall, by definition, the motion that results when the only force acting is gravity? So there you have it. 11 might be the easiest one of all. Falling with a terminal velocity. Well, in time, the faster an object goes, the greater force it has with the wind, and that begins to present a force opposite the direction of motion. But if the force of air resistance was smaller in magnitude than the force of gravity, there'd still be a net downward force and the speed would pick up. But because the speed picks up, then that makes the force become larger. So this process continues. The upward force gets gradually bigger and bigger and bigger and bigger, but at some point it stops accelerating. The acceleration terminates. And so we say it reaches the highest velocity it's going to get, what we call terminal velocity, and then at that point the force that represents the air resistance is just as long as the force that represents the gravity vector, and so the two cancel each other out, which means the net force then equals 0, and the acceleration is 0, but that doesn't mean the velocity is 0. The velocity is definitely not 0. The velocity just stops increasing, right? And whatever that velocity is what we call terminal velocity.